about 3 more lectures planned for now on characteristic classes. I wanted to start by sort of a leftover from last time. Namely, so last time we talked about homology and cohomology of BUN or BU, and we talked about the monomials in these BI as a good basis then for homology, and monomials in CI as a basis for cohomology. And we looked at the pairing, and then this was a non-trivial, an interesting pairing, non-identity, non-Kronecker pairing. And so what I wanted to then say, this is something that I wish I understood better, but it just hasn't come up in my research. The one also gets a basis of, in homology, fundamental classes, their images of Schubert varieties. You would need the singular have fundamental classes, but for most folks, you would prefer to use the smooth versions, but you can blow things up that you have these Schubert varieties mapping in, and that's a basis in homology. But you can also look at the same objects, and then we can talk about the Thom cohomology classes of Schubert varieties again. And now these are 4 different bases. They're all, of course, we can view them as somehow related to symmetric polynomials. All this story, for example, in cohomology maps in to the cohomology of projects of infinite projective spaces through the symmetric polynomials. But yeah, so what are these other 2 bases in relation for the first 2? Also, the first 2 was kind of funny because I related this pairing to a change of basis, so it'd be nice to kind of straighten that out a little bit as well. Okay, so what we're going to do this time I'm going to focus on the Thom isomorphism, and that's really something that I like to place with well, it is key in the theory of characteristic classes. As I'll mention, you can develop characteristic classes using the Thom isomorphism in various ways. They are key with different kinds of Poincare duality. There's a famous, a wonderful paper of Attia's that relates Thom isomorphisms to different kinds of dualities. I'm going to talk about the relationship to Steenrod operations and even to these basic Thom cochains, which we've been using a bit, but I think we'll reflect a bit more on those. So, Thom isomorphism. So let's define the Thom space of a vector bundle E. Here I'm, again, just using the total space to name the whole bundle as, if we're over a paracompact base, we can do this, look at the disk bundle modulo the sphere bundle. So that means, so I've got my bundle, and I'm going to look at the disk bundle, and then everything on the edges here, all these unit spheres, I can picture sort of coning them off. That's my kind of view as a Thom space. Rather than take the quotient, you take what's called the homotopy cofiber. You just cone off the subspace that you're trying to trivialize. This, if you want, is homeomorphic to the 1-point compactification of the total space if the base is compact. Because all we're doing, So that's sort of the standard thing where if the base is a point, then we're just looking at Rn, one point compactified as a sphere, or Dn mod Sn is a sphere. So, but if there's if the base goes off to infinity, then this then one point compactification will do more than identify the directions at infinity along the fibers. They would also identify things out at infinity of the base, and you don't want to do that. So a basic way at this is that if I'm looking at reduced cohomology or homology of the Thom space of a vector bundle, that's isomorphic to the cohomology of the pair, where I take the 0 is equal to the 0 section of the bundle. I think Milner and Stasheff call this E sub 0, but I'll say E take away the 0 section. And this is a module over the cohomology of E, because if you take a cochain which vanishes away from the 0 section, and you cup it with any other cochain, in other words, take a cochain and you cup it with any cochain in this relative group. Again, these relative things are cochains that must evaluate to 0 on any chain that lands in E mod 0. In other words, any chain that doesn't touch the 0 section, the cochain had better be 0. If you look at the definition of cup product, then cup product will let us cup together the cochain on E and this relative cochain which vanishes on E mod minus 0. So, so that's a convenient module structure. And then the one version of the Thom isomorphism theorem, using this, is that this, so the reduced cohomology of this Thom space, which as we said is the cohomology of this pair, is a free module of rank 1 over this cohomology of E, which also is the same as a cohomology of the base. And in fact, with a generator in degree equal to the rank of our vector bundle. So if it's an n-dimensional bundle, we've got a generator sitting in there and it's a free module. And that's going to be with Z mod 2 coefficients for any E, or with Z coefficients, or all with any coefficients for oriented E. Great. That generator in degree n is often called U. It would also be the image of 1 in the cohomology of E, or the cohomology of the base under this isomorphism. What do I want to say? Oh yeah, just free module rank 1. Of course, that just means that these are isomorphic as groups in particular. So the cohomology of the Thom space is the cohomology of the base, just shifted up degrees. So if I've got the cohomology of the base here sits in these degrees, then the reduced cohomology of the Thom space is going to just shift up. So this goes here. So anyways, that's clear enough. But but the point is that the cohomology of any space is a ring, and this is not an isomorphism of rings. It can't be, right? Once you shift things up, the degrees would get all messed up. It is, as we said, we've got this module structure, so you do have that bit of multiplicative structure around, but it's just one of these distinctions. Like Z is pretty, is there's an automorphism of Z with itself as a module over itself, namely 1 goes to -1. But once we have ring structure that there's only one kind of rank 1 object. So anyways, right. Oh, I meant to, back in the definition of Thom space, let me give you an exercise. Give you a couple exercises. Relate the Thom space of the vector bundle, B cross Rn to suspension in B. Are these the same space? And then the other thing is to say that the Thom space of the tautological line bundle over CPN or RPN, I'll say that for CPN, is homotopy equivalent to CPN plus 1. That's a fun fact. Okay, and then you can check that the reduced cohomology of CPN plus 1, if I get rid of that degree 0 class, that degree 0 generator, then those cohomologies match up. They're just kind of suspended twice, and same, well, right. Okay, and let me give an application before talking about the proof. And this will be a funny application in the context of this class, but I'd like to give folks an idea of how things, quote unquote, generally are done. Suppose I have a submanifold. And let's remember the tubular neighborhood theorem. That there's just some neighborhood of W which is diffeomorphic to the total space of the normal bundle of W. So what we're going to do is there's a collapse map. I'm just going to call it collapse from the manifold to the Thom space of the normal bundle. And what you do is you just take, well, this is, I claim, homeomorphic to M quotiented by M minus this neighborhood. So take everything outside of the neighborhood and identify it to a point. So that's collapsing everything outside of this tubular neighborhood of W. Alternatively, we can consider the pair. Let me just make that aside. So alternative, consider the pair M and M take away W. But let's, and again, by the tubular neighborhood theorem, then you can excise things and be thinking about the normal bundle and W. Okay, so what you can do is then if there's, let's think about this Thom isomorphism theorem. So by Thom isomorphism theorem, there's this key class in H, whatever the rank of the normal bundle, which is the codimension of W, and that's of the Thom space. And what is that? Well, it's the image of 1 in this isomorphism of that we're claiming is with this free module of rank 1 with the cohomology of W. So it would be corresponding to the unit class in the cohomology of W, but now it's this class in the cohomology of the Thom space. And then under collapse, and it's often, by the way, called U. That's what it's called under Milner and Stasheff. So under collapse, or pulled back via collapse, it goes to something. And I claim, and this should be clear enough in a moment, that it is the same class as the Thom cohomology class of W. So W has no boundary. And so, yeah. So that's a different way to construct cohomology classes from submanifolds. In fact, if we didn't like as much differential topology, notice that we just use the tubular neighborhood theorem. So we could prove the Thom isomorphism theorem, and we could define our Thom cohomology classes through this collapse map. We'd have to modify it similarly to how we modified the definition to allow for not just submanifolds, but things mapping. But that is entirely possible, and we could have used that technology to go from submanifolds, or again, our dependence manifolds we're sitting over our vector bundles, to cohomology classes, to the characteristic classes that we've been studying. You'll see in just a moment that in essence, so that would be perfectly logically possible. And then you could, the nice news is that the argument that we gave, for example, proving Whitney's sum formula through a more direct calculation, by first establishing it in the special case of products of line bundles, all that would go through. So this would be our definition of Thom cohomology class, and you could run the rest of the lectures off of this definition once we proved Thom isomorphism. We're not going to prove Thom isomorphism using Thom cochains, but so in fact, I think it's better to use Thom cochains to understand this Thom isomorphism. So in fact, the Thom isomorphism map can be at least partially, because we haven't talked about whether all cohomology can be realized by these Thom cochains. The jury, well, yeah, that's just another discussion, but at least can be partially defined through Thom cochains, through the Thom cochains we've been using. So let me give the picture there, the definition / picture. So I've got this, I've got my M, I've got my E, so I'm thinking about the Thom space of E, which is the disk bundle modulo the sphere bundle. So all of this I could think of as coned off. And if I've got some submanifold of M, so if this is W is a submanifold of M, well then, it's also a submanifold of E. It's also a submanifold of the Thom space. So what I can do is I'm going to send tau W to tau of, what do we want to call it? The inclusion of W. So this is really, I mean, W, remember, has, is mapped to M somehow. Maybe if I want some co-orientation. Oh, and I should talk about orientations. And so here what we do is we're just going to look at the inclusion of M in the zero space. So I could, in the total space, so that's like the zero section on M, composed with F. So notice that the codimension has increased by the rank. So that's good. And we now see that if E is oriented and W was originally co-oriented, then this IW is co-oriented. So this gives a sort of a immediate way to see that you need that it's helpful to have an oriented bundle in order for this to be an isomorphism over the integers. Okay. Note though that the Thom space is singular as I've drawn it. So you would either have to adapt the Thom cochains, which you can do. You can, there's only one point at which it's singular. There's one cone point, high codimension. So you can always assume that things are happening away from that point, so to speak, differential topologically. The other thing you could do is look and say a relative theory. The most convenient theory would be to, so we could consider the pair E and the complement of the interior of the disk. So say, I'll just say vectors of length greater than or equal to 1. So, so yeah, so you can do Thom cochains in a relative sense. This IW is going to vanish on any chain that is bounded away from the zero section. In particular, any chain that only lives in the vectors of has support in the vectors of length greater than or equal to 1. So it's a perfectly good relative chain, and you can you don't need to worry about a cone point in that case. Right. So I stated the Thom isomorphism in terms of a free module of rank 1, because there is something more, well, there's each of these formulations has some advantage, but let's actually connect to the statement given. So let's first think about what the Thom isomorphism, what this the generator. So let's connect to the standard statement. First, well, what is U in this model? So U is the generator. It corresponds to 1 in the cohomology of E, or the base. It maps to some module generator for this free module of rank 1. What is that? Well, 1 in the cohomology of the base M is represented by, so 1 in H0 of M equals the Thom class of the identity map from M to itself. It is M, right? W equals M. And so what is that going to go to? it's going to be the zero section, so I of m or 0 of m. So so that's U, is this this zero section sitting in there. It's related to the Euler class. So again, in various treatments of the subject, you see that the Thom class and the Euler class, there's relationships. Well, geometrically, both are given by the zero section. Next, if we note that E is homotopy equivalent to M, so we're supposed to take a cup product with a cohomology class in E. So let's consider some Y in the cohomology of E pulled back from our base M. So really what we're saying then is Y is going to be the a Thom class of our preimage in the bundle of some, say, W as a submanifold or pullback. And then what we're supposed to do in the Thom isomorphism is we're supposed to, Y is supposed to, then we consider Y cup U. That's Y goes to Y cup U is a Thom isomorphism map. Well, this is going to be geometrically, we now have the Thom class of the zero section, cup the Thom class of the pre-inverse, the preimage of W. Well, we've said that that's the Thom class of the zero section intersect the preimage of W. But that's just the Thom class of 0 of W. I mean, a little sketch, if you want, is that we're looking here at if locally, if this is the zero section of M, and then and I had some W, then the preimage of W is, because the vector bundle is sort of sitting over that, so this is P inverse of W, and the intersection of them both is, of course, just the zero image of M. That's pretty immediate, but I wanted to draw a picture anyway. Great. So we see that this definition agrees, this special case. Now, an important technical point is that if you wanted then to use Thom cochains to actually prove the Thom isomorphism, you would probably want some theory which said any cohomology class can be so represented. And that's something that, I'll be honest, I'm working out in a research paper now, what you need to do there. You're not going to represent any cohomology class by a closed submanifold, submanifold without boundary, or even a submanifold mapping to the manifold without boundary. That's various. That was a famous quote unquote mistake of Thom to consider that, and that actually started a lot of this interesting work. But and we'll talk about some of that work next time. But anyways, this at least illuminates why there should be such an isomorphism. Let me give two proof outlines. So proof one. Neither is going to be a full proof, but I think both have some. So let's suppose that the base B in the Thom isomorphism is a CW complex, then the claim is that this Thom space has a CW structure with one I plus n cell for every I cell of B, and if it's oriented, well, and you know, the cellular chain maps agree mod 2, or over Z if oriented. So the idea here is that you know, you have your cells in the base, and you look at the whole thing, and yeah, because over a cell, over the interior cell, the bundle has to be trivial, and so then if I look at the total space, it's going to be a cell of that higher dimension. You have those directions of infinity, but those attaching maps, except maybe down at the, you might have, you know, you'd want to pay a little bit of attention back at the dimension 1, but in fact, there's not much to be done, and in fact, you get this cell structure. So the idea here is that that the Thom complex of E is a twisted suspension, which with twisting, so but homology is at least mod 2, again over Z if oriented, is insensitive to the twisting. So if you step back for a second, you could almost be disappointed by this. One of the first things we did in early lecture is look at the sphere bundle and say, oh, that's one way to tell that this vector bundle isn't isomorphic to that vector bundle. They have different sphere bundles. Well, here, if you wanted to be sadistic, you could tell somebody, oh, well, maybe a good way to tell vector bundles apart is take their Thom spaces and just say, look at their homology groups. That's got to be interesting, right? That's got to tell us that some vector bundles are different from each other. But in fact, this Thom isomorphism theorem says that's a horrible idea as intended. But it's often the case in mathematics that you know, if things are isomorphic, then that can let you, for example, in our little application, that said that we always have this in particular, this U class, which is codimension n, and nothing, no twistedness of our bundle can get rid of that, and that would allow us, if we wanted to define Thom classes through this. And also, there's various proofs of Poincare duality and all sorts of other things which use the Thom isomorphism theorem. So on the one hand, you could be disappointed that these Thom spaces seem insensitive to the twistedness of the bundle, but conversely, and quite importantly, it allows us to actually make use of that isomorphism within other contexts. So I'm going to be, I think, even more brief for the proof outline number 2. It is basically the proof in Milner and Stasheff. And I'll just be so brief, I'm just going to say it's a 5-lemma argument. Now, the last time I taught algebraic topology, standard first year sequence, I told my students that you'll really sort of have mastered the elementary parts of the theory, which is maybe a bit of an oxymoron, but you'll really feel like you've you've arrived in terms of the basics of the machinery of homology, if you are comfortable when somebody tells you, oh, that's a 5-lemma argument, and you say, oh yeah, sure, I know what that means. So in this case, that would mean starting with this Thom isomorphism for trivial bundles. Remember that our vector bundles are trivial over open subsets, and then trying to glue them together via a Meyer-Vietoris argument. And then often, depending on, that's usually good enough for, say, a compact base or something like that. At some point in these 5-lemma arguments, and again, for example, Hatcher proves out Poincare duality and its sort of greatest generality in this way, you might have a limit to wrestle with. But the main thing is to go from sort of the trivial case to the global twisted case by sort of piecing these isomorphisms together. And if you can use Thom cochains, if we had the full cochain theory, it would be pretty clear that these Meyer-Vietoris sequences would be compatible. That's actually one of the biggest technical subtleties, is not that your Meyer-Vietoris sequences sort of, you have these pieces which look like they want to be put together with an isomorphism up here and an isomorphism down here, and but the hard part is to know that every little square commutes. But that would actually be pretty easy here with the way that we can define the Thom isomorphism map via inclusion rather than the cup product, which we have shown is equivalent. So I wanted to end with a little dictionary. So we've talked about, and again, there's a wonderful paper of Attia that relates Thom spaces and Thom isomorphisms to Poincare duality. Basically, if you have, you take Poincare duality, by which he also means like Lefschetz duality. You consider that duality theorem Alexander duality, which is basically, or Spanier-Whitehead duality, and then the Thom isomorphism, and basically kind of any two give you the third. You can all, these are very compatible isomorphism theorems. And as I said, we can even use the Thom isomorphism to define our Thom cochains, which are, if you will, or Thom classes. That's a manifestation of duality as well. Submanifolds and a compact manifold, submanifolds, we see their fundamental classes, that's homology. Through this Thom collapse, we also, again, can get cohomology. But I wanted to indicate how how the Thom isomorphism and these ideas related to Steenrod operations. Now, you might not have seen this, so let me say this is a theorem. I'm going to list both René Thom and Wu. I think some form of this is in both of their work. I'm not going to try to sort out priority. This is not to be confused with various Wu formulas for some of the Steenrod operations on and characteristic classes of tangent bundles. What I want to do is, again, let's consider just a submanifold with normal bundle nu. Then if I consider the characteristic classes of that normal bundle, and that's a characteristic in the cohomology of W. I could consider it in nu or W, but let's say in the cohomology of W. Well, either way. So, and then I apply the wrong way map, which, if you want, just says, well, let's take some sections of the normal bundle. Let's see where they vanish. That's a submanifold of W. But oh wait, W is a submanifold of M. So these dependence loci in W actually sit inside M, and I can consider their cohomology classes. The claim is that this is square I on the Steenrod square on the homology class represented by W itself. So the reason that I mention this now, and the reason that I talk about Thom as well as Wu, but if I had to call this anything, if I had to choose, I would call this the Wu formula, is that from the remark above, about how to that the Thom class was the image of the unit class in the Thom isomorphism theorem. Well, it's not a unit, it's not multiplying, but anyways, that class U in the Thom isomorphism under collapse, it suffices to consider this for Thom spaces. And then, well, I mean, we'd have to get into the definitions of Steenrod squares to prove it there, but I just wanted to mention that this is where that actually Miller and Stasheff sort of use this backwards from my perspective. You can then define the Stiefel-Whitney classes in terms of squares in this Thom space, but because you then have this Thom isomorphism to bring it back to cohomology of the base, if you will. But in fact, philosophically, I think of the characteristic classes as more fundamental than Steenrod operations. I think of two ways to come at Steenrod operations. One is through characteristic classes, as in this formula, and the other as through non-commutativity, through the equivariant extended powers construction of Steenrod. So Steenrod's original definitions, but this is some differential topology which came after Steenrod. And there's a paper of Quillen that I'd really like to understand much more deeply, which relates those two approaches to Steenrod operations. It's especially important if you're doing other cohomology theories. In fact, the characteristic classes approach to operations pushes through more easily. For the other approach, you would want to understand more about the cohomology of extended powers, and guess what? Yours truly is writing a paper on just the ordinary cohomology of extended powers. So there's a lot of wonderful things that are still to be worked out in some of these fairly classical stories. So I wanted to end, in light of this, with a sort of a dictionary. So this is no longer about characteristic classes, but how they led us to fill in this dictionary between geometry, so submanifold geometry, and cohomology. And it's right, it's not submanifold, because really we said you can associate such a class to anything, a manifold mapping to your base manifold. So we have, if we've got F from W to M, and then maybe we factor it through a bundle or a trivial bundle if we want to co-orient things. Then we get a cochain. One thing that you can take when you've got a manifold, if it has boundary, then you can take the boundary. And that corresponds to the co-boundary, right? So the co-boundary of tau W is tau boundary W. I think usually I find a minus sign natural there. And then Well, I mean, perhaps we can go back. These are cochains, and you can look at the disjoint union. And again, what this is via intersection is what's making this dictionary. So, but if I intersect with the union, my intersection points, you know, and again, let's make it basically disjoint union. But again, if it's not disjoint, yeah, union intersecting with union, I'm just adding up those intersection points. And we had things like the natural map. You can look at the preimage of W, and that's what the natural map in the cochain level is. But you can also, if you have a map, you can look at its image, and you need some hypotheses, some properness, but that's the Schriek map. So again, it's for the birds to apply duality and do a natural map and apply duality. What these wrong way maps are that these representing objects, and the wrong way map exists on homology as well. I can take the preimage of some manifold mapping in and get a new homology class. So it's just that yeah, the natural maps use sort of half of the story, either preimage or image, and then you get these wrong way maps in homology and cohomology if you, well, use the preimage or the image in the wrong way. And then the deeper part of the story, the more involved part, is you can look at intersection, and you have the fact that tau v cup tau w, I'm assuming that these have no boundary, is tau v intersect w. So you've got these submanifolds, you can take their union, you can take their intersection, that's all well and good. But the fact is that any submanifold has a normal bundle. And so we've got this formula that we just gave, that if you take the Stiefel-Whitney class of the normal bundle, that's going to be the Steenrod operation on the Thom class. So all this sort of geometry of these manifolds and well, the local geometry, this bundle geometry, has its impact, has its role in the cohomology story, and that's again something I'm trying to work out and even take this dictionary even further to well, the goal would be the full E-infinity structure, if you happen to know what that is. But yeah, so I'm going to stop there. I'm going to have another lecture on, well, now that we have Thom isomorphism, I wanted to revisit cobordism as an application of characteristic classes.